Let's consider a function f of x, just some generic function, and I'm interested in the area bounded by f of x on an interval a to b. Well, one way to approximate this is by simply slicing it into rectangles. And what I've done here is slice it into rectangles whose height is measured at the left end of the subinterval. So I would start at a and use f of a to get the height of the first one. Then I can move over one step and I use the left end of that subinterval to get the height of the second one, and so on and so on. And I'm not particularly interested right now in how many of these things there are. I'm going to say that I sliced it into n rectangles. So we slice into n rectangles. Then I'm interested in the width of each rectangle. I'd like to be able to express that mathematically, and I'm going to call that a delta x. And that would be the width of the entire interval divided by how many subintervals I chopped it into. I also would like to have a name for each of these steps along the x-axis, each of these x values. And so one way to do it is to start by saying a is x0, and then I'm going to take n steps to the right, and b is going to be xn. I'd like to get an expression in general for what the ith position is, because ultimately here we're going to try to turn this all into summation notation and get area approximation as a sum. So the ith location here, I'll just look somewhere in the middle, is going to be my starting point plus how many steps I took to the right. So x naught plus I delta x. Then I can start to express the total area of all these rectangles put together and say that's approximately the shaded area that I was trying to get at the beginning. And the area of the first rectangle is going to be f of x0 times delta x. The area of the second rectangle, f of x1 delta x. And so on and so on. I add together the areas of all these rectangles, and at the very end I have to be careful because the height of the last rectangle, the nth one, is measured one step before xn, so I'm going to have an f of xn minus 1 delta x. Written in summation notation, this is the sum as I goes all the way from 0 to my finishing value of n minus 1. F of xi, that's the height of the ith rectangle, times delta x, the width of each of these rectangles. And again, delta x is computed by taking the entire interval width and dividing by how many rectangles you chopped it into. One last thing I want to point out here is that because f of x is increasing and we're measuring the height of each rectangle at the left end of each subinterval, I can see that my rectangle approximation of the area is underestimating the true area. Let's apply this to the function e to the negative x squared, and the reason I chose this one is because all you can do with this function is numerically integrate. There's no symbolic antiderivative for it, so you have to use some kind of approximation technique. And I'm trying to get the area under it on the interval 0 to 1 using n equals 10. In other words, I'm going to slice into 10 rectangles, and I'm going to measure their height at the left end of each subinterval, so I wrote LHS for left-hand sum. There's my n equals 10 approximation, and one of the first things I have to do is figure out what's the width of the subintervals here. So the width of the whole integration interval is 1, or 1 minus 0, and then divided by how many rectangles I want to slice into, and I get 1/10 for that. Then I'd like to write down an expression for the ith cut point. So this would be x0 here on the left. This is x1, x2, and so on and so on and so on. And eventually I get to xn, which in this case is the 10th cut point. The height of my last rectangle should be measured from the 9th cut point. So my ith cut point is given by the starting point, which is 0 in this case, plus I steps to the right, I delta x, or I could say I times 1/10. Then my area approximation, I'm going to write it in expanded form one more time. It's going to be f of x0 delta x plus f of x1 delta x, and so on, all the way until I get to the last one, which is 1 less than n, because I'm measuring the height from the left end of the subinterval. And that'll be x9 delta x. And now I can write this in summation notation as the sum from I equals 0 to 9 f of xi delta x, or sum of, as I goes from 0 to 9, e to the negative xi squared. So I'm going to plug in what xi is. It's up here. I could write it as I over 10 squared times delta x, which is up here. It's 1/10. And this is a sum that you can compute in a computer algebra system or with a TI calculator. And I'm going to use Maxima to get it done. Here I am in Maxima. And I've written the sum as the sum of 0.1, that's instead of writing 1/10, times %e, that's the special symbol for e in Maxima, to the negative I over 10 all squared as I goes from 0 to 9. So that's how the syntax works. If you want a decimal approximation, then you write float out in front, hit Shift Enter, and I get an approximation of 0.778-ish. Now, one thing I wanted to point out as we wrap this up is that e to the negative x squared is decreasing on the interval 0 to 1. So I can see by measuring the height of each rectangle at the left end of the subintervals, I'm overestimating the true area. So if you want to get an extremely accurate area on this, we could use a numerical integration algorithm in Maxima. Here we are in Maxima, and I'm going to approximate this integral by using the quad QAG function. Remember, %e is the special symbol for e, and I have e to the negative x squared as x goes from 0 to 1. And the final 1 there is just the algorithm in quad QAG that I chose. You can choose any number from 1 to 6. And they're all extremely accurate and fine for our purposes. I hit Shift Enter, and I get a better approximation. So a better approximation of the area is 0.747 using quad QAG. And as I expected, our rectangle approximation was overestimating by a little bit.